Welcome to Learn with us. This is the 16th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about IV characteristic curve of Zener diodes. You understood states of Zener diodes, cases of Zener diodes, and in your last lecture, you also understood how you are going to determine status of Zener diodes. It means you understood how you will find whether the Zener diode is in breakdown region or not. What are the learning objectives of this lecture? In this lecture, you will understand what are bipolar junction transistors, and you will also study about types of bipolar junction transistors and their modes of operation, where you will understand working of transistors. Now, what are bipolar junction transistors? The bipolar junction transistor is a three-layered semiconductor device having three terminals. First terminal is base. It is lightly doped and very thin region. This base avoids recombination of charges. Second terminal is collector. It is moderately doped region. Third terminal is emitter. It is the most heavily doped region. Now here this bi in this name indicates this transistor has two types of charge carriers. First is holes and second is electrons. Okay. There are two basic types of BJTs on the basis of their construction. It means the construction of BJT basically describes the physical arrangement of the semiconductor materials from which they are made. First type is NPN or N-type BJT. In this type, majority charge carriers are electrons and minority charge carriers are holes. And the second type is PNP or P-type BJT, where majority charge carriers are holes and minority charge carriers are electrons. Now, look at this figure. This is NPN or N-type BJT, which has two layers of N-type material and one layer of P-type material, which is base. So this is first terminal, this is second terminal, and this is third terminal of this N-type BJT. Now look at this. This is PNP or P-type BJT, which has two layers of P-type material and one layer of N-type material, which is base. So again, this is first terminal, this is second terminal, and this is third terminal of this P-type BJT. Now we will look at the electrical symbols of N-type and P-type BJT. Now look at this. This is the symbol of N-type BJT. where an arrow is here, and this terminal is collector, this terminal is base, and this terminal is emitter here. Now look at this. This is the symbol of p-type BJT. Now this arrow is here in this type, and this terminal is emitter, this terminal is base, and this terminal is collector. Now in both of these types, the currents from these three terminals are IB, IC, and IE. Now if you look at this n-type BJT, the current IC flows in this direction, the current IB flows like this, and the direction of current IE is like this. Okay. Now here in this p-type BJT, current IE flows in this direction, and this is the direction of current IB, and this is the direction of current IC. Okay, so these are the electrical symbols of n-type and p-type bipolar junction transistors. Transistors have two major functions. First is to amplify, and second is to switch. It means a bipolar junction transistor acts as an amplifier or a switch depending upon its mode of operation. This bipolar junction transistor is a current controlled device. If a signal of small amplitude is applied to the base of this transistor, then this signal in the amplified form is available at the collector of the BJT. This is the amplification provided by this bipolar junction transistor. It does require an external source of DC power supply to carry out the amplification process. A transistor can be operated in three modes. First is an active mode, second is cutoff mode, and third is saturation mode. In active mode, BJT works as an amplifier, whereas in cutoff and saturation modes, BJT acts as a switch. Now, there are two junctions in bipolar junction transistors. First is collector base junction, and second is emitter base junction. Now look at this figure. We know that this is NPN transistor, and here this is collector base junction, and this is emitter base junction. Now in case of PNP transistor, this is emitter base junction, and this is collector base junction. When transistor is in active mode, the collector base junction is reverse biased and the emitter base junction is forward biased. Now look at this figure. We know that in NPN transistor, this is collector base junction, which is reverse biased in active mode, and this is emitter base junction, which is forward biased in this mode. And here voltage will be VB, in collector voltage will be VC, and in emitter voltage will be VE. Now if you look at this figure, then in active mode, this VB is greater than VE, and this VC is greater than VB in case of NPN transistor. Okay. Now look at this PNP transistor. Here this is emitter base junction, which is forward biased, and this is collector base junction, which is reverse biased in active mode. Now here in this case, this VE, because here we know that voltage is VE, here voltage is VB, and here voltage is VC. So in this case, this VE is greater than VB, and this VB is greater than VC. Okay, so this is the condition of PNP transistor in active mode. It means this is representing forward biased condition, and this is representing reverse biased condition. Okay. Now we will understand working of transistor in active mode. We know that this is NPN transistor, where this emitter base junction is forward biased and this collector base junction is reverse biased in active mode. And we also know that in forward biased condition, depletion region is thin, whereas in reverse biased condition, this depletion region is thick. It means this region is thin in emitter base junction here, and it is thick in collector base junction in active mode. Now we know that this emitter terminal is made up of N-type material in NPN transistor, and this emitter is heavily doped. It means this emitter has a very high density of conduction band or free electrons. Now these free electrons, they will easily diffuse through this forward biased emitter base junction, and they move into this lightly doped base region. Here this base is made up of p-type material, and we know that p-type material has holes as a majority charge carriers, but since it is lightly doped, it consists of very few holes. So some of these electrons that are coming from this emitter region, they recombine with the holes that are present in this base region, and they flow out of this terminal. Now this constitutes the base current IB, which flows due to recombination of electrons and holes. We know that the direction of conventional current flow is opposite to that of flow of electrons. It means this is the direction of base current, and this is the direction of emitter current. Now the remaining large number of electrons, they will cross this reverse biased collector base junction, and they will constitute the collector current, and this is the direction of this collector current, that is opposite to that of flow of electrons. So this is the working of transistor in active mode. Now we will understand transistor in cutoff mode. In cutoff mode, collector base junction is reverse biased and emitter base junction is also reverse biased. Now look at this. It means here in this NPN transistor, this collector base junction is reverse biased and this emitter base junction is also reverse biased. Similarly, in PNP transistor, this emitter base junction is reverse biased and this collector base junction is also reverse biased in cutoff mode. We know that here we have VC, here we have VB, and here we have VE. Similarly, here we have VB, here voltage is VE, and here voltage is VC. So in case of NPN transistor, the condition would be VB is less than VE and VB is less than VC, and in case of PNP, VE is less than VB and VC is less than VB. It means this is the condition of reverse biased junction. Again, this is the condition of reverse biased junction here. Okay. Now we will understand transistor in saturation mode. In this mode, collector base junction is forward biased and emitter base junction is also forward biased. Now look at this figure. It means in this NPN transistor, in saturation mode, this junction is forward biased and this junction is also forward biased. Similarly, in PNP transistor, this emitter base junction is forward biased and this collector base junction is also forward biased in saturation mode. Now here we know that voltage is VC, here voltage is VB, here voltage is VE, and here voltage is VE, here voltage is VB, and here we have VC. So in case of NPN transistor in saturation mode, VB is greater than VE and VB is greater than VC, and in case of PNP transistor, VE is greater than VB and VC is greater than VB. So this is the condition of forward biased emitter base junction and this is the condition of forward biased collector base junction. Okay. Now we will understand how transistor acts as a switch. As I have mentioned earlier, transistor acts as a switch in cutoff and saturation modes. In cutoff mode, both collector base and emitter base junctions are reverse biased, and we know that in reverse bias condition, no current flows through the device, hence no current flows through the transistor. Therefore, the transistor is said to be off and this transistor acts like an open switch here. Now we'll talk about saturation mode. In saturation mode, both collector base and emitter base junctions are forward biased, and we know that in forward biased condition, current flows through the device, hence electric current flows through the transistor. Therefore, the transistor is said to be in on state. Now look at this circuit. This is an NPN transistor. As you can see here, this N-type material of this emitter region is connected to the positive terminal of the battery, and again here in collector region this N-type material is connected to the positive terminal of the battery. It means in this case there will be attraction of these electrons towards these positive terminals. So it means here this condition will be reverse biased, and again this condition will also be reverse biased here, and as a result of this attraction the depletion region will become thick and there will be no flow of current through the transistor, which will make this transistor off. Okay, now look at this circuit. As you can see here, this N-type material is connected to the negative terminal of the battery. Similarly, in collector region, this N-type material is also connected to the negative terminal of the battery. It means in this case there will be repulsion because we know that like charges repel each other. Now this condition will be forward biased, and in this case this condition is also forward biased. So as a result of this repulsion, this depletion region will become thin and there will be flow of current in this circuit, which will make this transistor on. So this is how a transistor acts as a switch. Now we will understand some equations that we will be using for solving transistor circuits. Now look at this figure. We know that in this NPN transistor, current IE flows in this direction. This is the direction of current IB, and the current IC is flowing in this direction. Now if we look at this point, here one current IE is leaving and two currents IB and IC are entering. So if we apply Kirchhoff's current law, here we are talking about NPN transistor, then we'll get this equation IE is equal to IB plus IC, where this IE is leaving and these two currents they are entering. Okay, now we'll talk about PNP transistor. Again, if we look at this point, we know that this is the direction of current IE. Current IB is flowing in this direction, and this is the direction of current IC or collector current. Now again, if you look at this point here, current IE is entering and current IB and IC are leaving. So if we apply Kirchhoff's current law here, we get this equation IE is equal to IB plus IC, where this current IE is entering and these two currents they are leaving. It means in both NPN and PNP transistors we are getting this equation. Okay, now look at this figure. As you can see in NPN transistor, this base is at higher potential than this emitter. So here voltage drop in this emitter base junction will be VBE. Okay, once this transistor is in the on state, the voltage drop between base and emitter is VBE, which is equal to VB minus VE, and it is assumed to be 0.7 volts if we're talking about NPN transistor. So here in this case the equation of collector current will be IC is equal to IS e raised to the power VBE divided by NVT. As you can see, this equation is similar to current equation of diode. Okay. Now, in case of PNP transistor, this emitter is at higher potential than this base. It means here when this transistor is in the on state, the voltage drop between emitter and base is VEB, which is equal to VE minus VB, and it is also assumed to be 0.7 volts. And in this case, the equation of collector current will be IC is equal to IS E raised to the power VE V divided by NVT. Okay. So this is the equation of collector current in case of P-type or PNP transistor, and this is the equation of collector current in case of NPN or N-type transistor. Okay. Now, as you can see here, both of these potentials are positive. We use negative signs when wrong terminals are at higher potentials in that particular type of transistor, like if this base is at higher potential as compared to this emitter, then in this case the voltage drop VEB will be equal to minus 0.7 volts. Okay. Our third equation is IC is equal to alpha IE, where this alpha is common base current gain. If we rearrange this equation A, we get alpha is equal to IC divided by IE. It means this alpha is the ratio of the DC collector current to the DC emitter current. Typically, the values of this alpha range from 0.95 to 0.99. This alpha is always less than 1. Why? Because the collector current is always slightly less than emitter current by the amount of base current IB. It means if collector current IE is 100 and base current IB is 1, then from equation 1 we know that IE is equal to IB plus IC. It means IC is equal to IE minus IB. In this case it is 100 minus 1. It means here collector current is 99. So alpha will be IC divided by IE, which is equal to 99 divided by 100. It means this alpha is 0.99 in this case. Okay. The fourth equation is IC is equal to beta IB, where this beta is common emitter current gain. Now, if we rearrange this equation B, we get beta is equal to IC divided by IB. It means this beta is the ratio of the DC collector current to the DC base current. Typically, the values of beta range from less than 20 to 200 or higher. Okay. Now look at these examples. If you have base current IB 50 microamperes and if collector current IC is 3.65 milliamperes, then how you are going to find beta and collector current IE? For beta, we will use equation 4, which is IC is equal to beta IB. It means this beta is equal to IC divided by IB. Now if we put values here, we get 3.65 milliamperes divided by 50 microamperes, and after solving this you will get beta is equal to 73. Okay. Now how you are going to find collector current IE? For this you will use equation 1, which is IE is equal to IB plus IC. Here IB is 50 microamperes and IC is 3.65 milliamperes, and after solving this you will get IE is equal to 3.70 milliamperes. So these are your answers here. Okay, this is example number 1. Now if you have beta which is 200 and if base current IB is 50 microamperes, then what would be collector current IC? Again you will use equation 4, which is IC is equal to beta IB, and here beta is 200 and IB is 50 microamperes. Now after solving this you will get IC is equal to 10 milliamperes. Okay, so this is your answer. Okay. Alpha and beta are two important parameters that are used to analyze a bipolar junction transistor circuit, but alpha is a less used parameter as compared to beta in transistor circuits. Now, what is the relation between alpha and beta? This alpha is equal to beta divided by 1 plus beta. This is equation 5. Now, if we rearrange this equation, we get alpha 1 plus beta is equal to beta, and it is equal to alpha plus alpha beta is equal to beta, and it is equal to alpha plus alpha beta minus beta is equal to 0, and here it is equal to beta alpha minus 1 is equal to 0, and if we rearrange this equation we get alpha is equal to minus beta alpha minus 1. Okay, So now this equation becomes alpha is equal to beta 1 minus alpha. It means here this beta is equal to alpha divided by 1 minus alpha. Okay, so this is equation 6. These equations are showing relationship between alpha and beta. That's all for today. Now, what are the key takeaways of this lecture? In this lecture, you understood what are bipolar junction transistors, and you also studied about their types and their functions as well as modes of operation. You understood how transistor acts as an amplifier and how transistor acts as a switch. In this lecture, you also understood some current equations that you will be using for analyzing transistor circuits.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.